Hello, my name is Samuel Schlafer. In this lab report, I'll be presenting experiment 1 from Physics 2212, amount of excess charge on an ordinary object. In this experiment, I'll walk through the physics behind it, the computational models, and what we discovered. The purpose of this lab was to determine how much excess electric charge is on a piece of charged Scotch tape. Ordinary materials can pick up excess charge through contact or separation, a process called transfer, but how much charge? In principle, it's somewhere between 1 electron and roughly 1 times 10 to the 5th coulombs, which is a rather large range. By doing a simple experiment and building 2 computational models in GlowScript, we were able to narrow down that specific estimate and find that there's approximately 7.07 times 10 to the negative 6 coulombs per piece of tape. And now let me show you how we got there. There are 3 core physics ideas at play here. First, electric charge. Matter can carry excess or positive or negative charge. Like charges repel, opposite charges attract. Charge must be conserved, though. It's transferred and not created. Second is Coulomb's law, which gives the electric force between 2 point charges. F equals 1 over 4 pi epsilon naught times Q1 times Q2 divided by R squared. The constant 1 over 4 pi epsilon naught equals 9 times 10 to the 9th in SI units. And then third is force equilibrium. When tape B floats motionlessly above tape A, its momentum isn't changing, so the net vertical force must be 0. This means the upward electric force equals exactly the downward gravitational force and gives us the equation we need to solve for Q. We also made 2 key simplifying assumptions because one is that both tapes carry equal charge, which is reasonable because they were peeled from the same base tape, and that each tape's charge can be treated as a single point at its center. In section 6.1, when we brought 2 U-tapes near each other, we expected repulsion since both should carry the same sign of charge. In practice, the tapes showed minimal but noticeable deflection, which could be due to partial discharge or humidity. When brought near a neutral object, nothing happened, which was expected. In section 6.2, we determined the sign of the charge by using a plastic pen rubbed through the hair, which we know becomes negatively charged. And when we brought that pen near the U-tape, the tape was attracted to it, telling us the U-tape must be positively charged. Now for the quantitative experiment in section 7.1. Our system is tape B, the floating tape. The surroundings are tape A, below, and the Earth. Since tape B's momentum isn't changing, the net Y force, like we said earlier, is 0, so electric force up equals gravitational force down. And so here are our measured values. Tape length is around 20 centimeters. Tape 1 is 1 gram per meter, so mass equals around 0.0002 kilograms. Separation begins at around 2 centimeters, so the gravitational force is around 0.002 newtons, and that means the electric force is also equal to 0.002 newtons. So with these measurements, we can solve for Q. Step 1, we know gravitational force, like we just said, is 0.002 newtons. Step 2, set the electric force equal to this gravity, and then use Coulomb's law, F equals 1 over 4 pi epsilon naught times Q squared over D squared to solve for Q squared, and then we're able to see the force, which multiplied by the D squared divided by the Coulomb constant. So once we do some conversions and plugging in, we get Q equals approximately 7.07 times 10 to the negative 6 coulombs, and that's approximately 4.4 times 10 to the negative 13th excess electrons on each tape. Excuse me, 10 to the positive 13th. In section 7.2.1, we asked what fraction of the surface atoms contribute to an electron. Since the tape is essentially one-dimensional, we estimate the number of surface atoms on the tape, length divided by the atom length scale, so 0.2 meters divided by 10 to the negative 10th meters, which gives us around 2 times 10 to the 9th atoms, meaning roughly 20,000 excess electrons per surface atom, which seems rather high, which reflects the rough nature of our approximations, treating the tape as purely one-dimensional and assuming all of the atoms are uniformly spaced. This is a picture of a computational model, assuming point charge. Again, we made some really rough estimations and assumptions, which leads to our pretty inaccurate results of how many excess electrons per piece of tape. Our second model uses line of charges starter code. So instead of 1 point charge for tape, we use n equals 10 charges evenly spaced over the 20 centimeter tape length. And then eventually we're able to find the net electric force on the top tape. We then tune Q until this force balanced gravity. Comparing the two models. So point charge model gave approximately 7.07 times 10 to this negative 6 coulombs. Line charge model gave somewhat different value. Line charge model is probably more physically realistic since the real tape charge does spread along its length rather than just at a point, and it better captures how the geometry of the charge distribution affects electric force. So some what ifs. What if electrons were positive and protons were negative? Physics would just be identical with signs flipped. And then some conclusions. To summarize, we determined that a charged piece of Scotch tape carries approximately 7.07 times 10 to the negative 6 coulombs of excess charge, corresponding to about 4.4 times 10 to the 13th excess electrons. This is a tiny fraction of the tape's atoms, but a physically meaningful and measurable amount. The line charge computational model is more accurate than the point charge model. Thank you for watching.